good to see all of you, though. Good morning to you. Got a good group. We tried to put this thing at this time of day because of reaching it all the way across Texas. We had a different time zone, so we wanted to make it where most people could still attend, or at least use it on their smartphones or something while they're in the field, for those of you that may be working. But again, welcome to all of you for being here this morning. I'm going to go to Wayne and switch it over to him. You can send me a comment or ask you questions, and I will try to answer those either at the time, or we'll do it as we keep going, or at the end of the meeting here. So give me a minute. Let me find Wayne. I got so many of you thumb through right now. Find him.
Okay. Good morning, everybody. Thanks for joining this thing. This is a first for me. And Paul's keeping things going. I should have the first slide up here of my presentation. As usual, I got about 4 hours worth of slides, but we got 1 hour worth of doing. Okay. Some things we want to talk about is some basic electrical information. And this is basic electricity that everybody's, oh man, I don't want to hear that again. But I'm going to tell you where I got the information that I've been thinking about this ever since Paul contacted me, and what am I going to talk about? So I watch what happens when people call in with their questions or text the questions in, and they get 400 or 500 responses. And I look at some of those, and some of them are pretty good, and some of them are terrible. And I'm really concerned about the people that are really interested in knowing the facts, and they get a bunch of crap. So it is what it is, and you know it. I'll talk to you about it. Anyway, I'm going to go over some things directly from the code. We can have some questions later that can be off the subject, and I'll answer off the top of my head and what I know. But if we need code references for things that I say, well, you've got my numbers now. You can contact me, and I'll be glad to look it up, give you some exact code numbers, because if you are dealing with these electricians out here, they want you to prove up everything you say. And the code is very amazing because it can prove up what you say. The code is an installation book. Well, there I am on my first slide. It says where the electrons come from. This is a concept that I've used for a long time to kind of explain electricity. And we know that it comes from Ohm's law, EI and R, volts, amps, and resistance. But I look at the beginning of the circuit, and we're going to look at a circuit. The beginning of the circuit is what I call the pump. And you see I got that pump jack over there as my example. But the pump is the transformer. Every circuit starts with the transformer and could be traced back to that transformer that is putting out the hot wire, if you will, and it's going out to the load, and then back to the transformer, and we'll look at that more clearly. Back to the transformer is very important, and I think that sometimes we don't understand that, but it is very important. The neutral can shock you, the neutral can kill you. The neutral is very important. If you get in that circuit, then you become part of the circuit. That's not a good thing. Now, we're looking here at some distribution and transmission. If we start over here on the right-hand side, starts out at the power plant. The first thing it does, it goes into a transformer that, again, we're calling the pump. And it's raising the voltage from the voltage that comes out of the generator, alternator, raising it up to a high voltage, 300,000, 500,000, whatever it may be, and then goes out over the towers and comes into a substation someplace. Well, that's the area there in your neighborhood somewhere with a big cyclone fence around it, with the transformers sitting out there and all the overhead electrical stuff. And then it's divided up into circuits that leave the substation. But at that point, the real high voltage that's transmission drops down to a distribution voltage. And so it can come down to the two main volts and come across on the poles. The two main voltages that we deal with for the distribution voltage is 7200/12470. And that means it'd be like these, you're looking at the pole and the wires. If we were going from the hot wire to the neutral, it would be 7200 volts. Or if we go line to line, it's 12,470 volts. And it's distributed 3 phases. And the other is the new, and not so new now, but the higher distribution, where the lower voltage from hot to neutral is 19,920 volts. The line to line is 34,500 volts. You said, man, that's a lot. Well, yes, it is, but if you'll look, that's running down the street, it's running underground, it's running out maybe behind your house, and yeah, that's high voltage. It's 3-phase, 19,920 to ground. And it's up on poles, it's underground, and it's very dangerous, extremely dangerous. I know some linemen that said if there was a pole line like that behind their house, they'd move. But anyway, it is what it is, and it's what the power company had to do to increase the distribution to more and more homes and businesses and whatever. And then it hits the final transformer. In this case, it's up on a pole, and it's coming down to the dwelling unit. So it steps down to 120/240. That's single phase, 3-wire. Now that's one we're normally talking about in residential wiring. So you're going to get 120 volts from hot to neutral or from hot to ground, and you're going to get 240 volts from line to line. Let me show you right here. This is called single phase. It is not 3-phase. And when the wires come into your panel, they come in line 1 and line 2. It's not phase A and phase B because it's only single phase coming out of that transformer. Another phase of the high voltage goes down the street to another line of transformers and houses. So each street gets a high voltage wire of 7,200 to neutral or 19,920 to neutral, and then it's stepped down to 120/240 single phase. Now it's called 3-wire because it's the 3 wires went into the house. You're familiar with them: line 1, line 2, and the neutral. And that's what the power company brings in for the distribution to the home. But the wire that comes into that home or business, but we're going to talk home. The wire that comes in, that's 120/240, comes from a transformer. That pump jack I have out there on the pole is the transformer. And let's be sure about this. Whatever comes out of that transformer, meaning the voltage, the line voltage that comes out, goes to the house, goes through all your appliances and everything in the house, comes back to that transformer. I want you to understand that in concrete. It don't go away. It comes back to the transformer that produced it. And of course, that's a basic circuit where we're coming from a source, we're going out through a load, and we're returning back to the source, and it's a closed system. Now, we have a ground coming out of that transformer that's connected to the neutral point out on the pole that goes down to the butt of that pole. It's called a butt ground, and it comes around the bottom of that pole and up the pole to the neutral point of that transformer. Then over at the house, you've got your grounding electrode, and your grounding electrode conductor feeds it. So there is actually a connection can be made between ground rod and over to the pole, and up to the pole, back to the neutral of the transformer. And so remember what I'm saying. What comes out of that transformer has to come back to that same transformer, and it's a closed circuit. It's not going to go to another transformer. If we had this same pole line parallel to what's coming in here, and we had another house and another transformer, they're not going to intermix. The output is from the transformer to the load and back to that transformer. Many don't understand that. They think the voltage comes out and just goes somewhere and don't come back. Well, if you get in the middle, if you get in that circuit anywhere, and it goes through your body, you're going to get a shock. And right here, before we go too much further, remember, guys, 120, any voltage that we're looking at on this slide is multiplied times 1.414. And that's the peak voltage. So what your meter reads is like 120 or 240 or 7200. But what's really happening, because we're talking about alternating current, and we'll look at some sine waves in a minute, the peak voltage is 141.4% higher. So that 120 volts that we're dealing with, that we think is, oh, it's just 120, it's not a big deal, is 169.7 volts. If we get hung up on our touch 277, we're looking at about 400 volts, 395 volts right there. So that's why you always remember, if you got it in the length of the 277, you really got 400. If you get 120 volts as you're messing around, you're really getting 169.7. So that's the voltage that your body feels. That's why it's very, very important to not get involved with it, because it will kill you. It only takes 100 milliamps going through your body to start the killing process, 100 to 200. Okay, let's go to, all right, here's a pump that's sitting out in the yard here in Sienna Plantation area in Houston. This transformer's a pad mount. It's sitting out in this guy's yard. Big houses with big yards, swimming pools with about 100 yards away from it. If you'll see on this transformer, it's got 100. That's its kVA, kilovolt amps output. This is its output of the transformer. And if you look real close above 100, it's 19.9. So this is an underground distribution at 19,920 volts, sitting out on this pad in this fellow's yard, and 100 yards away is his brand new swimming pool. So we had to do some special grounding out there just to be sure. It's not, you're not supposed to have any voltage stray coming around, but you want to be sure. These are dangerous. You don't let your kids play on them. You don't let your animals play on them. And these things can actually give you a shock through a phenomenon called capacitive, a capacitive action that can shock you. So you stay away from these transformers. The light company messes with them, and that's their business. And normally the transformer's just fine. You crawl all over that box and there's not a problem. But what about inside? You've all seen snakes, you've seen ants, roaches, all kind of stuff can get inside that box, and that can cause current to flow through these varmints over to the box and cause some problems. So give these things real respect. So here we have this particular transformer feeds this one house, and out in this subdivision, they just have one transformer per house. A lot of transformers normally feed 4, 5, or 6 houses that you'll find in subdivisions. But out here, they just got a transformer for well, it's two houses, each transformer for two houses. And your secondary comes off of this transformer underground over to the house. It's 120, 240, single phase into the house, into the main panel, through the meter in the main panel, and is distributed to the branch circuits in the house. Now, if this acts right, we're going to have a circuit. We're going to talk about it. This is an animation that works on some things, but it may not work today. Oh, okay. This is line 2. I'm calling it the red wire here. We got a black and a red, line 1 and 2. Line 2 is coming out of the transformer. It's going up. It's going through the meter. It's coming through the panel, through the main breaker, through a branch breaker. It's going over to this big blue valve. That's a refrigerator. And then it's going through that, coming around, back to the panel neutral, down through the neutral conductor, over to the transformer. Now we have a completed circuit. We have the hot, and we got current flowing. That's the little arrows and stuff. But I want us to look at the refrigerator. Another part of this story and my concept in teaching electricity is the load. The load is the resistance of whatever you're supplying. In this case, it's a refrigerator. It's got refrigerant compressors and lights and stuff. So the load is a valve. Think about it this way. The valve controls the amount of current that will flow. So if it's coming at the voltage is 120, it gets over to this load, and the electricity goes through the pumps and everything, the compressor and everything, and then comes out, back to the neutral, returning back to the transformer. So the load is the valve controlling the flow of current. Oftentimes it's said, and we're supposed to understand that a load, and remember now, a load is any appliance, any equipment that you're supplying, is drawing current. All right. How many amps is it drawing? Well, look at it just a little bit different way. It's not drawing anything. Drawing, pulling, sucking the current. No, it is controlling the amount of current that goes through that load. So loads don't draw, pull, or suck. They control the amount of amperage that goes through and completes the circuit. If it's your body, your resistance may be, if you're wet, it's going to be 100 ohms of resistance is what we use. And in death cases, we use 500 ohms as the valve, if you will, or the load that the victim gets in series with and goes through their body and can hurt or kill. So our voltage is pressure. It comes from a pump. The pump's a transformer. It goes through the wires, and you know our plumber friends have got us on that. You know, bigger pipe, more water, smaller pipe, less water. Well, we know that's the same thing with electricity. The bigger wires is made out of more electrons, and so you can have more current flow. And then it goes through the controller, and that's the valve that whatever you're supplying will control the amps to whatever value that the engineers designed the controller to be. Remember, our appliances and the loads that we feed and that we supply comes from a factory somewhere. They're built under engineering supervision. They're tested as they run out the back door to see and put a nameplate on it. And that load has, that nameplate says the voltage is supposed to work at and the amperage that's supposed to be controlled, and often the wattage and all other kind of values. That's if everything is working perfectly. And so we've got this perfect machine coming out of the plant. We put it out in the field, we hook it up, and that's where we screw it up. because then it's left up to the power company or the electrician. And so we have the National Electrical Code. That's an installation manual. Yes, it's for safety, but it tells us how to install listed equipment that's born in a perfect condition, and we take it out in the field, and we're supposed to hook it up and make it work, and then deal with it if it don't work. The electricity will flow in the path that we give it. That's our job. And so we think of any load is the resistance that's controlling the flow of current. Now, I'm going to short this thing out by mashing the button. So if we look over, and I've got a green wire connected to the refrigerator, and that's called the EGG, or the equipment grounding conductor. And so it's going to, hopefully, yep, here comes a short circuit, and it comes to the grounding conductor, comes over to where we've got it connected at the neutral bar in the panel, or ground bar. It's coming down through the grounding electrode conductor to the electrode in ground. It's going through the earth. It's coming back up to the transformer, and up at the transformer, we have the ground wire inside the transformer is connected also to the neutral wire. That's called the XO lead inside the transformer. So that completes the circuit. Now, in a short circuit, we have current coming back through the equipment grounding conductor to this bar, and say, well, it goes through the ground wire back, yeah, but it also goes back through the neutral wire. So anything that's coming back to this bar will find its way back to the transformer, either through the neutral wire, which is the best way. Emphasize right now, the ground is the most important thing you have on a service. And you know how bad grounds are. The ground rod is bad, the clamp is bad, and all of that. I'm going to tell you, if you've got a low impedance ground, you're going to save your service. Surges and all kinds of things will be prevented by having a low resistance. All right, here we have a transformer at a Walmart store. Matter of fact, the guy got hurt on this. Panel blew up in his face and knocked him off the ladder. He got burned a little bit, but he's okay. Here's one in a doctor's office in a multi-story building, and it's in there just pumping away, if it would. It's taking the 480 volts, three-phase, down to 120/208, three-phase, going to a doctor's office down the hallway. This doctor was a plastic surgeon, so he's real particular about how his instruments work, because most of his work in there is women that's having things done, and he wants his instruments working really good. And so we want to be sure that he didn't have a problem there. This is the inside of that transformer. You can see it down at the bottom there. It's a 75 kVA 480Y/120-208 three-phase, four-wire. Okay, so now it's supposed to be written this way also. 480 with a Y, that's WYE, down to 120-208, three-phase, four-wire. We've got three-phase 480 coming in, and we got 120-208 going down the hall to the doctor's office. And grounding is done in there properly too. I need to move on. I see that our time's going. Here's actual graphs of voltage and amperage. And of course, we're talking about alternating current, AC. We're not dealing with DC, so we got AC. And we have three phases. So we have phase A, B, and C. And this is an actual, you show the chart on the side is a voltage reading of the voltage 0 going up to a peak, back down to 0, going off, coming down to a peak, and back up again, alternating the actual recorded voltage. And then at the bottom, we're looking at the recorded amperage. And this is the amperage that was being supplied to the doctor's office at this particular time. And those of you that's been into this, you can see because this sine waves has dimples up on the top, they're not flat. They should be nice and pointed, but they're not. They got distortion up there, and so that is harmonic distortion in the system. Sometimes this causes a problem. In this case, it didn't, but if it was dealing with some sensitive equipment, this would be very important. The current actually goes, if you'll follow it, it goes up and then dips down a little bit and goes up just a little bit and then comes on down again. Well, that harmonic distortion is recorded that way. And this is what I needed to know to make, to clean this system up and get that distortion out of there. So we needed a recording of what's actually going on. Now, let's look at the code. I know sometimes you have codes and sometimes you don't, but especially taking a look at them and reading what it says. So I want to do some reading, and we're going to have to do it pretty quick, but this is the purpose of the code, 90.1. Look at it real close. This is what we're out here about. The purpose of this code is the practical safeguarding of persons and property from hazards arising from the use of electricity. This code is not intended as a design specification, even though we use it for that, or an instruction manual for untrained persons. Well, we think about what is a trained person? Well, that's an electrician. Well, maybe yes, maybe no. The actual definition of that is one that is thoroughly knowledgeable in AC and DC theory. How does electricity work? And that's why I started off with the pump and the valve and that sort of thing. If we know how electricity works, then we can install it safely according to the information given to us in the code. Our code is well over 100 years old. Hundreds and hundreds of people have been involved in putting it together, and hundreds have died and have been hurt. That generates rules that needs to go in the code. This is a long-term thing over many, many years. It's a lot of intelligence going on in there, and a lot of respect should be put on the code. Adequacy. The code contains provisions that are considered necessary for safety, because this is a safety book. Compliance therewith and proper maintenance will result in an installation. We have an installation book here that is essentially free from hazard, but look, not necessarily efficient, convenient, or adequate for good service or future expansion of electrical use. We're not required to add anything for future. I'm talking bottom line now, minimum stuff. You can always add more, and that's a good thing, but by the code, that's all we're talking about right here. And they make an informational note that hazards often occur because of overloading of wiring system by methods or usage not in conformity with this code. Guys, that's where you're at every day. You're looking at methods that are not in conformity with the code, and you're picking out these problems, and you're saving people's lives, and you're saving people's homes. And I'm telling you, as I always have, if it has not been for the home inspectors and what you're doing, our world would be in a whole lot worse shape, and our homeowners would not be safe. There's agencies supposed to take care of it, but a lot of times that's not done. Thank God for the home inspector. This occurs because initial wiring did not provide for the increase in the electricity. Okay. An initial and adequate installation and reasonable provision for system changes provide for future increases in the use of electricity. Now, this is an informational note. It is not a law. This is saying, hey, pay attention. Go ahead and add a little bit to it, but you don't have to. Informational notes are not law. They're just good ideas and thinking that we need to jog our mind a little bit and help us as we go along to understand some things. Now, Authority having jurisdiction, an organization, office, or individual responsible for enforcing the requirements of the code or standard, or for approving equipment, materials, installation, or a procedure. Well, it's interesting to note that the authority having jurisdiction can be not just the electrical inspector that comes out. There's many things. I won't read through all of this, but the one down at the bottom, I want to, it's inspectors and fire department and health department and all of these insurance can be designated as an authority having jurisdiction. But look at this bottom one. In many circumstances, the property owner or his or her designated agent assume the role of the authority having jurisdiction. Now, we have places all over the state that do not have a incorporated city. We're out in the county somewhere, and even though the state of Texas license for all over the state of Texas, the electrical inspectors that work for the state are just a few, and they can't inspect stuff. And in these subdivisions and whatever, many times the builders say, well, I'm the builder and I'm the authority having jurisdiction and you will do it my way. Well, that's not necessarily so. If you own that house and you designate somebody that knows what they're doing, you can become the authority having jurisdiction. So there's a lot of argument can go on right there. But I just want to point it out because I get involved in this. Often I get called in and get designated as the authority having jurisdiction. I kind of don't like that, but on the other hand, I'm just trying to help when I can. Special permission. The authority having jurisdiction may waive special requirements in this code or permit alternative methods. But here's the key, where it is assured that equivalent objectives can be achieved by establishing and maintaining effective safety. This does not mean just because somebody's got the wild idea that something needs to be done, that it's going to be okay. Can you assure that this is equivalent to what the code says? And also, will it establish and maintain effective safety? Maintaining could be corrosion. You can't, a lot of times you got to watch out about that. And we argue a lot of times about putting antioxidant on aluminum. Well, in the new stuff, it's not required, but there are places where it would be needed to maintain effective safety. So also for the authority between codes, our code comes out every 3 years. It's generally on the books for about a year before it's really starting to be enforced, even though the state of Texas will adopt the 2020 code September 1 of this year. We will be under the 2020 National Electrical Code. We're on the 2017 now. I also been made aware that the IRC that a lot of people use, I'm particularly not real familiar with that, but it adopted the 2014 National Electrical Code. And I've had builders say, well, I build under the IRC and the 2015 IRC. Well, that's fine, except that's the 2014 code. I mean, that would be today. So you have to kind of learn how to deal with that. A lot of times you say, well, I want to bring it up to code. Well, that may or may not be something that you can back up with good reasoning. Installation and use. Equipment that is listed, labeled, both shall be installed in accordance with any instructions included in the listing or labeling. Put this down on your hot sheet. You can look at an installation and you can see crappy stuff all over it, and you say, man, this is not what that's designed for. They're using the wrong fitting or no fitting or whatever. You can go back to 110.3b and call it out. That is not according to the manufacturer's instructions. And the manufacturer puts this out at the factory and has to be listed or has to be tested by a recognized testing laboratory and the label stamp put on it, and that makes it legal to be put in the code. I want you to know, if you don't have the listing, if you don't have that label, you know what I'm talking about, that somebody made out in his garage or whatever, it is not illegal by code. And here's the code, like it or not. Well, I built that at home. Well, you've done a great job, but where's your stamp? Well, I don't do that. I just made it. Well, okay, that's your business. So to us, the electrical field, we got to see the label. And you know the old saying about if it don't say UL, well, it's not good. Well, there's lots of labels. We use UL, ETL, and CSA. If it's labeled by some of those, go for it. It's okay. There's a lot of other stuff around. These are approved testing laboratories that take stuff, put it through the works, try it out, short it out, blow it up, do whatever they need to do to see how safe it is, and then put their label on it if it's okay. Field labeling can be done. Things can be done in the field, and people from UL or ETL can come to your place. This is normally commercial and industrial. They can look at this piece of equipment and put a field label on it. It don't have to go to the factory or back to the lab. It can be done in the field. The code now is loosened up a little bit in the 2017 and 2020, allowing some field modifications, but we have to be real careful. The electricians are very clever and very, they want to change things. They want to drill a hole where there's not supposed to be a hole, and come up with some great ideas to do things. But the point is, the material you're looking at, the equipment, is listed for what it is, not for what you change in the field. Bootstrapping, I've got to get on. This is a bad thing. On your tester, it may show up 2 yellow lights. Bootstrapping is when you don't have a ground wire, your 2-wire system, you're coming from the neutral, you loop it around and hook it to the ground post right there. So whenever you plug in a grounded cord cap, you got a hole there for ground, except that's not. That goes to the neutral. I've done death cases on this. Beware, this can kill. Keep jumping to things. I guess we need to do that. But in grounding, we want to look at 250.4A in the code. And I don't know how that jumped over some things, but get a code book. People say, well, where's the main rule about the grounding here? 250.4A, 1, 2, 3, 4, 5. Now, we missed 1 and 2, but grounding and bonding, information about that is listed in 250.4. You can look this up on the computer, but like bonding of normally non-current carrying conductors that may be in a conduit system. 4, bonding of conductive material that are just likely to become energized. And the main thing about the whole story is number 5, effective ground fault current path. Remember that path we drew a while ago from the appliance back to the transformer, actually back through the panel and the transformer. Electrical equipment and wiring and other electrical conductive material likely to become energized shall be installed in a manner that creates a low impedance, low resistance path, facilitating the operation of the overcurrent device or ground detector for a high impedance grounded system. Shall be capable of safely carrying maximum ground fault current likely to be imposed on it from any point on the wiring system where a ground fault may occur to the electrical supply source. Here again, getting that short circuit current back to the breaker, and it says the earth shall not be considered as an effective ground fault current path. I worry about this when our electricians are out there running 14 gauge wire 250 feet through a house or somewhere, and that's the equipment grounding conductor. It's that little bitty number 14. The resistance is going to be so high it will not trip the breaker properly. And that is, and we can make a case, and have made a case, that that is against the code. But anyway, that's when worst come to worst. Let's move on. Grounding of service supply systems. A premises wiring system is grounded by AC service shall have a grounding electrode conductor, look at here, connected to the ground edge. That's a neutral service conductor at each service in accordance with 250-24A1 through A5. Now, when you bring that neutral coming in from the power company, it will connect to the ground. And as you go to your ground bar, that's where you get your neutral connected to the ground right there in the panel. Now, this is on the supply side. On the load side, I hope we'll have it. Yeah, look at number 5. Load side, a grounded conductor shall not be connected to a normally non-current carrying metal parts of equipment, to an equipment grounding conductors, or to be reconnected to ground on the load side of the service disconnected means. Folks, this is why we need 4 wires from the main panel to sub panels. You got to carry the ground. You cannot connect neutrals and grounds together anywhere except at the main panel. So as you go downstream, that grounding conductor is basically a separate system by itself. It's not it's required and necessary, but you don't connect it to anything else, just to grounding as you go all the way along. Okay, here's a fellow friend of mine. Look at here. He was checking this. He was talking on the phone, and he's checking voltage here inside this panel. And he's got his voltmeter there. He's got a ring on. His hands are naked. This panel is hot. You can see on the meter it's got voltage there. And my little deal up in the top left, these people are beating each other on the head because this is wrong. It shouldn't be this way. We need to be protected. Now, we do not have to be dressed like this to work on a residential service. But I do want to point this out. If you're in commercial and you're in places where you're going to have higher ground fault current, this is what you need to have. You have your hard hat with a shield. Behind the shield, you have safety glasses, both. You have earplugs in. An explosion will blow your eardrums out. You have flame retardant suit. This is just flame retardant. It's not a space suit. This is a minimum type suit. And you go down to, you got rubber gloves that are insulators, and you got canvas gloves that are over the rubber, and the canvas protects the rubber. If you're dealing in a panel and you've got that thing open, you got wires going everywhere, you know it's hot, and you're poking around in there with your finger, you ought to at least have the rubber gloves on. You can wear the rubber without the canvas if you don't think that there's anything in there to snag the rubber. You don't want any holes in your rubber gloves. But you should have that, you should have your glasses, and you really should have a hard hat. Your hair burns real fast. And so this is not so much for the home inspector, but it is OSHA and safety code. Okay, that's all of that. I got a whole lot more, but we're out of time.